Today we're going to be talking about the number of tornadoes, this example in which the number of tornadoes obeys a poisson process and averages one every 3 months in this location. We want to talk about a different variable, which is different than the number of tornadoes. It's the time t until the next tornado. So something very subtle is going on here. The number of tornadoes is discrete. Its outcomes is one tornado, two tornadoes, three tornadoes, of course, zero tornadoes also possible. But the time, t, that's fundamentally different. That's continuous. It can be zero point 0.3, it can be 0.817 units of time. So the time t is what's called a continuous distribution. And we want to relate these two. So here, uh, I'm being asked in the first problem to calculate the probability that t is less than or equal to 5 months until the next tornado. This is of course equal to 1 minus the probability t is greater than 5. And this is a key thought process, but the first occurrence of the tornado will take place after 5 months, only if no occurrences of the event are recorded in the interval. So here's the key fact. The next occurrence will not take place after 5 months, only if there are no occurrences (0 to 5). Okay, and since the number of occurrences is Poisson, this means that we're going to be asked to compute the probability that x is 0, where x is the Poisson probability. So this is the key thought process. The probability that the time is bigger than 5 is equal to the probability that there are no occurrences, where x is the number of occurrences in a 5-month period. Okay, and that's a key process. So this is going to be equal to, just using the Poisson distribution, is going to be e to the minus lambda times lambda to the 0 divided by 0 factorial. Okay, so we need to just write down what is lambda. So lambda is the average, not in a 3-month period, so one tornado every 3 months, but it's in a 5-month period. So 5 over 5 times 1/3 times tornadoes per month, and this is going to be 5/3 of a tornado per 5 months. Okay, so that's the value of lambda. And so the probability that t is greater than 5 is equal to e to the minus lambda, which is minus 5/3. Okay, okay, so that's the first calculation of probability that we're asked for. Um, so we're not quite done with 1, right? So probability t is less than or equal to 5, of course, is going to be 1 minus probability t is greater than 5, and that's going to be 1 minus e to the minus 5/3. Okay. Okay. For the second one, this is asking about the distribution. We're going to use a key fact, which is the distribution, which is equal to f of t. That's the derivative of the cumulative distribution. So f of t, that's the probability t is less than or equal to little t. And remember, this is about time. This is the probability of time until the next occurrence is less than time t, lowercase t in this case. And we can set t equal to 5 months, for instance. And this is going to be 1 minus the probability t is bigger than t. And using the same logic that we used before, the probability that t is bigger than t means there are no occurrences. So I should say it's equal to the probability x equals 0 and means there are no occurrences in the interval 0 to t. Okay. And here x, that's the number of occurrences in the time interval uh, of time t. And I'll put months here. Okay. So probability x equals 0. Again, that comes from a Poisson. That's going to be e to the minus lambda times lambda to the x, which is 0, divided by 0 factorial. This will be e to the minus lambda. Lambda is going to be equal to 1/3 of a tornado per month, but we want it to be in a period of t months. So we're going to multiply by t over t. So this is t over 3 tornadoes per t months. Okay, and so this will be e to the minus t over 3. And so now, if we go back up, the distribution is given by 1 minus e to the minus t over 3. If we want to get the density, all we have to do is differentiate this cumulative distribution function. So this tells me that the density is equal to f prime of t, which is going to be 0 minus e to the minus t over 3 times the derivative of the inside, which is minus 1/3. That's going to be 1/3 times e to the minus t over 3. And we can recognize that this is what's called an exponential distribution. And so this illustrates this theorem And this theorem says if we have a Poisson process with parameter lambda, then W has an exponential distribution. With parameter beta equal to 1 over lambda. And beta is the expected value of W. Okay, so this is to highlight this theorem, and I should also say W is the time of the next occurrence of this Poisson process.